Hey, Mr. Forden here, and you had a little word problem today in class. And word problems, they're complicated, but a lot of you guys fought through it. I see a bunch of people working on it right now. You're doing homework, trying to make sense of this here. So, hey, I figured I'll just go through the whole thing with you. It's kind of hard to draw it out and visualize it. Perhaps you got there, perhaps you didn't, but hey, let's do it together. Let's kind of go over it over the next, I don't know, hopefully 20 minutes, hopefully no longer than that here. We got fireworks here. That's right. Fireworks, they explode, they give us a show. And that's what's kind of like complicated about this one is because the question in this problem is how long will it take for the firework rocket to hit the ground? And if I'm thinking about fireworks correctly, you want the firework to explode at the vertex, right? So it explodes in air. It's never really going to hit the ground. So I guess the idea is like, how long is it going to take to land on the ground if it weren't exploding? I don't know. Anyways, that's why it's important to kind of visualize things first. So anyways, maybe I'll go back to show you how I visualize the problem. This is the way that I think that works here. I got this here, ninth grade class, you little freshman here. Sorry, not to call you little freshman, you big freshman. The ninth grade class will be putting on a fireworks show. They're going to launch the fireworks from the school tower that's 80 feet above the ground. There we go. We got 80 feet. Okay, so it's launched from 80 feet. And the rocket's going to rise with a speed of 64 feet per second. I don't know if that's really going to be necessary, to be honest. So it's going to go 64 feet per second, and then it's probably going to go faster. I don't know. I don't know why they tell you that. I don't think it's that important to go across the field. But yeah, it's eventually going to end up on the ground. This problem is you got to figure out how long it's going to take to end up on the ground. And if we're doing this based on height, that's going to be 0. That's going to be one of your zeros of your parabola, okay? So the question is where you launched it from also another 0? No, it's not, because again, you're launching from 80 feet. So the parabola is already kind of set in motion there, right? A lot of times this happens, right? You launch something, I'm on the second floor of my home, okay? I throw something 5 feet up, okay? 5 feet up from where I am. Does that mean my vertex is going to be 5 feet high in the air? No, it's going to be 5 feet plus however high I am. And then it's going to crash to the ground. So you got to it's not going to get launched very far this way compared to how much it'll come down. It's an additional 80 feet down. So anyways, your x-intercepts here, probably got an x-intercept here, probably an x-intercept here. So it's not going to be at 0, right? It's going to be at something negative is going to be one of your x-intercepts. This is going to be something positive. So anyways, let's keep going through it, because it turns out that your graph that you're going to have to create is kind of similar to what I just sketched out here. This is actually the flight path of the whole thing, but we want to do it related to time, okay? Height related to time. So my time 0 is right here. This is time 0. Oh, it hasn't blown up yet. It blows up at the vertex, right? It shouldn't blow up over the football field and then potentially be following a parabolic path to actually land if it didn't blow up. But if it blows up, the firework's gone, right? What's going on here? So anyways, kind of a silly problem, I guess. But anyways, this isn't going to be an x-intercept. This is going to be a what kind of intercept here? It's going to be a y-intercept, okay? Y, well, the height above ground, we're going to start at 80 feet. Okay, you don't actually have to draw this in. Ignore the little fireworks things. Let's maybe turn the fireworks thing off. Let's go with just clicks here. All right, because my parabola is probably going to look more like this. Time since launch in seconds, height above ground in feet. Well, I know at time 0, okay, if my time is 0, my height is 80 feet. Okay, my height is 80 feet. And then I'm launching it over the football field. There we go. We know because of gravity, the forces of gravity, what goes up must come down unless it explodes. Unless it explodes right here, which it would, right? It would explode there. Anyways, what goes up must come down unless it explodes. So I guess we care about how long it takes to not explode and end up on the ground. Or maybe it's going to explode here. Maybe this is where the big explosion is. Fireworks they explode in the air. What's happening here? Okay, so this is it. So we got an x-intercept here. That's what we want to know. We want to know, but we're going to measure from time 0. That's what we're going to measure. It's ultimately going to solve the problem, okay? And then you might happen to know what your other x-intercept is. Although that's just like an unnecessary point. It just gives you sort of a parameter of this parabola. It's not necessarily something where it's going to tell you anything, because it doesn't get launched on the ground. It gets launched from the tower, okay? So that's what makes this problem a little bit harder to understand, a little bit more challenging, okay? So anyways, think we need to, well, I don't know, figure out x-intercepts could help. Still wondering what the equation is, perhaps. Perhaps you wrote that down. Okay, number 8. Ooh, they gave us the equation. That's very nice here. Our ninth grade class will launch a fireworks. Look at people moving around. I like this. Ninth grade class will launch the fireworks from the school tower of 80 feet. go 64 feet per second, go across the ball field. And here's an equation. They give you the equation for us, okay? You don't have to generate the equation here. X represents T. What is that here? T represents, should be T represents T. The time in seconds, Y, or H of T, okay? So H of T is what we've got a function here. Input of time, output is height. So that's why it's H of T here. It represents feet above the ground. How long will it take the firework to rocket to hit the ground? Well, let's do this. We got to figure out when, in the context of the problem, the firework is on the ground. And that's going to be a 0, right? That's going to be a 0 of this actual equation because we care about when height is 0, right? We care about height is 0. That's when it's on the ground is when its height is 0. Let's figure it out. And then we got to figure out which of our 2 times it's on the ground is when it's actually on the ground. Because remember, it doesn't start on the ground. It ends on the ground, a certain positive seconds away, right? Positive seconds away from launch, okay? From launch here. So anyways, first order of business, we should probably change H of T to 0. Why? What does H of T represent? It represents the height. We care about when height is 0. And if we can change H of T to 0, then we can solve for T. We can solve this equation. This is about solving quadratic equation. Solve for T, which is the time in seconds it would take to be on the ground at 0 height. So that's what it's recommending to us here, okay? So we have this here. We want to get our zeros of this equation because that's going to be the height off the ground. This is all pretty complicated, isn't it? Pretty complicated. But chunk it up one step at a time. What have you been doing recently? Oh, we're doing the zero product property, okay? What is that? Well, it's solving for x-intercepts. Solving for the zeros of this polynomial right here are going to be the x-intercepts of the parabola. And that's what we care about in this problem, where it hits the ground. So I'm going to flip y to 0, right? Remember, an x-intercept is the value of x when y equals 0. Here, y is represented by h of t. Here, x is represented, our input variable is t here, okay? So I'm going to have 0 is equal to negative 16 t squared plus 64t plus 80, and I'm going to solve that equation. I'm going to solve that. How do I solve an equation like that? What's one method we've been studying recently? The zero product property, okay? So zero product property. So this is something that I said. So you could zero product property. Remember, it means change it to factored form. Solve for the values of t that's going to make each of the factors equal to 0, okay? Because anything times by 0 equals 0, right? 4 times 0, what does it equal? Equals 0. 0 times negative 7, what does it equal? Well, anything times 0 is 0. It equals 0, okay? So we're going to use the power of 0 to solve an equation like this, called the zero product property, solving by factoring, okay? So what you could do is figure out the factors, because if you can get a 0 factor, and you'll see what that means in a second if you're having trouble following this from Friday's class. If we can get a 0 factor, right, we know what we can plug in for t to make one of the factors 0. That would make y the output 0, which is what we want. We want height, h of t, to be 0 because we want to know when that parabola, when that firework ends up on the ground. Remember, I guess it doesn't explode. All right, so anyways, doing this equation, here's our generic rectangle down here. You can put it in here all you want. Negative 16t squared and 80 right here. Okay, you can do that if you'd like. Problems with that, though. Wait a second, what's the next step? Remember, your generic rectangles, if you can build a rectangle out of it, which you can, this will be factorable. What do you got to do? Well, you got to remember that trick that if you have a rectangle, a built rectangle, then the diagonals would multiply to be the same product. This diagonal would equal, the product of this would also equal the product of that, right? And this is where you put your t terms, okay, here. So this is a little rough because 80, see out here, like the top of my rectangle, what do I got to do? I got to do, oh, that's some geometry. I got to do negative 16, and I got to multiply it by 80, and all of a sudden, I got 1280. That's a freaking huge number. That's really, really big. So what some people I saw doing in class, which is great, is they were trucking forward. They were trying to figure out, here's my product, negative 1280. Here are the amount of t's I have to work with, 64. And they were seeing this, and they're like, oh, I'm going to do it. I'm going to figure out factors of 1280 that also add up to 64 to help me factor this. Okay, do you think that's the smartest way to do this? To this factoring? It might be an easier way to do this? There is. There definitely is. There's certainly an easier way to do this. And that is either factoring out common factors or something mathematically you can do right now. So try to watch me real quick here to make your life a lot easier. I know, stay with somebody after class to talk about how they did this, and they did a good job. What I can do to my equation, because remember, how do I use zero product property to solve for x-intercepts? Step 1, change y to 0. Value of x when y equals 0, that's an x-intercept. Or value t of my input variable is the value of t when y equals 0. So what I can do, I have an equation right here. One thing I can do that's a valid move for an equation is I can divide both sides by the same thing, right? I know I have two things equal to each other. That's what an equation is, equality, right? I'm trying to find something that's going to make my input for t's that makes y equal to 0. So anyways, if I got two equal things here, I can divide this side by 2 as long as I divide that side by 2 to keep my equation balanced. So I can divide both sides of an equation by the same thing to preserve equality. Beautiful thing about 0, if I divide 0 by anything, okay? If I divide 0 by anything, not 0, divide 0 by anything, what does 0 divided by anything equal? It equals 0. So what I can do is I can divide this left side by whatever the greatest common factor is of all these terms here. What I pointed out to you at the end is I noticed something. 16 does go into 64. Goes into 64 how many times? 4 times. 16 also goes into 80. Well, 15 goes into 75, right? You get that in your heads pretty quickly, right? 15 times 70 times 5 would be 75. So that means one more 5 is 80. So 16 times is how many times 5 would go into 80. So 16 goes into 85 times, okay? So what I can do is I can technically divide both sides. I can divide both sides by 16. Check this out here. I'm going to divide both sides by negative 16, okay? That's going to help me because I like my squared. This is just me. It's personal preference. I think I make fewer mistakes. I like when my squared term, my t squared term, remember these are all terms. Terms are separated by addition or subtraction. I like when my squared terms, the coefficient is positive. That makes factoring for me a little bit easier. So that's what I'm going to do to both sides. I'm going to do completely valid mathematical move. It's called the division property of equality. If I divide one side of an equation by one thing, as long as I divide the other side of the equation by the same thing, then equality is preserved. We end up equaling the same thing. It's like a scale, right? Scale. Divide by a certain amount, divide by the same amount, equals, right? And then we're good to go. Okay, divide this by negative 16, and now let's do it. Let's just simplify this before we actually do the zero product property. Okay, 0 divided by negative 16. Well, 0 divided by anything is 0. So 0 doesn't change the left side. Beautiful thing about 0. Okay, here, negative 16 t squared split negative 16 ways. Well, we just divide the coefficients. We're going to have t squared here, okay? Positive 64 divided by negative 16 would be negative 4, right? A positive divided by negative is a negative number. So negative 4 times negative 16, yep, that would equal positive 64. So I'm going to have this be negative 4 and then t, negative 4t times. So here, just the numbers. Divide into the numbers, right? And we have to worry about the variables. Okay, negative 16 goes into 80, negative 5 times. So there we go. That's what we practiced last week, and now we just got a word problem. Just like, hey, checking out a little context how this can work here today. And I want to go through it with you guys right now. Okay, so now we have this. It's written in standard form, but it's also simplified too, right? Just simplify it a lot. I can simply factor this, solve for my zeros. I think down here it says write your solutions here. I think they mean solutions for this once you've changed the equation to equal to 0. Not the solutions to the problem, just the solutions for the zeros or the roots or the x-intercepts. It's what the 3 different words we have for x-intercepts or for the zeros of a polynomial or the roots of a polynomial. Anyways, lots of language in math here. It can be kind of overwhelming. Okay, so follow my lead here. So if you follow this, we're good to go. If not, if you have them with big numbers there and you're able to figure it out, great, good for you. But I'm doing it this way, okay? Let me build out my generic rectangle. T squared, and then I'll put negative 5 right here. So then my diamond should be pretty easy to make here. Negative 5 times t squared. Remember, this diagonal, multiply it. That's your product you're looking for the t terms, what you have right here, 64t. So I got to get him to multiply to negative 5t squared. Excuse me, not 64t. I simplified it up here. And I have negative 4t's which wish to work. There we go. Negative 4t right there. And now we play the diamond game. So how am I going to break up my t's along this diagonal so that they add to negative 4t and that they multiply to negative 5t squared? Well, I'm going to have t in both. Let's put t here. I'm going to have t. Drink my tea in both situations. The heck is wrong with me? Why am I saying stuff like this? Okay, so negative 4 is my sum. My product's negative 5. So when they're one apart, here's a little trick. When they're one apart, it's going to be whatever this number is and 1 here. Okay, and 1 here. What do I get? Do I get negative? Is this going to be positive 4 or negative 4? Negative 4. There you go, okay? When your sum is only 1 away from the product, that's just a little shortcut. Take the product, and it's going to be the product on one side, its coefficient, and then and then 1 for coefficient on the right side, for instance here. And then you got to decide how your signs work to make it all work out. Does it work out? Does it check out? Yeah, it does. Negative 5t times 1t is negative 5t squared. Negative 5t plus 1t is negative 4t. So I'm going to go put this into my freaking generic rectangle, and I can factor. I can totally factor this now. So here, t squared, I always start with that one. T times t. So I got my sum that's over here. I remember using these generic rectangles just by typing, so we all have the same workspace here. Kind of uniformity, we call it here. Anyways, t times t is t squared. How do we get to negative 5t? Well, it's minus 5. How do we get to, did I write something wrong here? This should be, this is just 1t right here. That's fine. And then plus 1. There we go. Okay, so here we go. I am now writing this in factored form. Okay, so here they should have said in the directions, write your solutions for the zeros of your polynomial, or this polynomial here, this equation here, because the zeros, using zero product property, you had to use that today because we're doing new skills. The zeros is the way you do it. You figure out that's where my x-intercept is going to be, and that's going to allow me to answer ultimately the question. Okay, so here and I know this is kind of what they're getting at. They're looking at what are the solutions. Solutions a lot of times quadratics is your roots, your zeros, right? Solving for when y is 0, just is what it is. Here, okay, so let me get this. We got factors. My factors here are t minus 5 times by t plus 1. So now we got our zero product property. Okay, zero product property. Let's do that to solve for t. Okay, so I know that t minus 5 times by t plus 1 multiplies together to become 0 if I'm solving for an x-intercept, the value of t when h of t is equal to 0, right? That's why the 0 is there. So zero product property is going to get us two solutions to this equation, right? Two solutions to this equation. So remember, if any factor within a product is equal to 0, that product has to be 0. Right? Anything times 0 equals 0. So here I have t minus 5 times t plus 1. That means there are two possible solutions that could make this right side equal to 0. First solution is if that, t were 5, right? If t is 5, okay, we got 5 minus 5 times by 5 plus 1, and that would just equal 5 minus 5 is equal to what? Equal to 0. And 0 times by, it doesn't matter, it's 6. 0 times by anything equals 0, okay? So one of my solutions, positive 5. Other one, negative 1, okay? Here's how we solve these, okay? Just because these were easy to solve, but just remember, what I do is I want to take my t minus 5, I just set up another equation with it. I say t minus 5 is equal to 0, so t equals 5 is one solution for this equation. Okay, when you finally solve a quadratic equation, a lot of times you're again just flipping to 0, solving for the roots, solving for the zeros here. It's confusing in textbooks. They'll just say solve this quadratic equation. You're like, huh? What does that mean? Solve for a 0. It's short for it, right? Short for solve for 0. Okay, and then I got t plus 1. T plus 1 equals 0, right? Because remember, there's another thing. If t plus 1 is equal to 0, that's also going to make y 0 once I multiply. So t equals negative 1, right? T plus 1 equals 0. Subtract 1 from both sides. T equals negative 1 is a second solution to this equation. Okay, right? A zero, right? It's looking for the zeros, or the roots as they're called, or the x-intercepts of the parabola. What you're spending a lot of time doing here in this advanced calculus arm of math. This is a calculus arm. This isn't quite calculus, but it's like something you need to study before you go into calculus later on in life here. Okay, so there are my answers here. My answers are 5 and -1. Okay, go ahead and submit it. Good, I don't have to explain. It's nice when you just submit your answer. Like, I already done it. It already explains here. Okay, is there anything else I need to say about this? I feel like there was something else I need to say, but anyways, let's move on. All right, so I got my answers, my solutions here. T equals 5 or -1. How we can use this to solve the problem. 9th grade class, let's do this here. How long will it take for the firework to hit the ground? And, well, it's on the ground after 5 seconds. It's also on the ground at -1 second. What do you think that means? Oh, that's kind of messy. I think let's go back to the actual problem, is that this situation here just has a domain of 0 seconds, and now we've proven to 5 seconds, because once you hit the ground, you can't go down anymore. So only one of these x-intercepts is actually relevant, right? Relevant in this problem here. So here we launch it. We launch it at, remember, this is at 0 seconds right here. Okay, this is 0 seconds. All right, we're at 0 seconds. Okay, 0 seconds. Okay, 0 seconds right here, gets launched, and then it ends up on the football field after 5 seconds. There's your answer. What's the deal with that other x-intercept of being -1? Well, that means that if we had launched it from the ground on the identical parabola, instead of starting by launching on this on top of this tower, and we matched, so basically if we launched it to the tower and it maintained the same speed as we launched it from originally the tower, and we matched this exact parabola, then -1 second ago it would take 6 seconds in total, right, to actually go here, okay? We launched from here, though, so we only care about one of our x-intercepts. This actually didn't happen, okay? The domain of this particular situation is just what you see in green right here. 5 seconds. That's it, okay? And I can see it here on this graph. Yeah, there we go. This here, right, because x equals 5 is an x-intercept. There we go. That's where it blows up, I guess, if we're letting it hit the ground before it explodes. And then here, -1 would be another x-intercept down here, but it didn't actually get launched from there, right? So this is not part of the domain. I don't need to show it here, okay? Even though this equation here, you would know where that x-intercept was if we didn't restrict our domain at all within our word problem or within whatever we're doing here, okay? So let's go ahead and answer this question here. The firework will hit the ground 5 seconds. There we go. We did it. Yeah, hopefully you did it too. Hit the ground 5 seconds after it was launched from the tower. We know this because when t equals 5 in the equation, because, okay, the variable, I'm going to explain the variable. The variable t represents the number of seconds since launch, right? Isn't that how they defined it? Number of seconds since launch. It proves, justify thoroughly here. How long will it take? Well, let's see here. T is the time in seconds, I think, since it's launched. I think we can safely assume that. Number of seconds since it was launched. Okay, when t equals 5 in the equation, h of t equals 0. We used the zero product property to solve, okay, which confirms 5 seconds after launch, the firework hits the ground. If it didn't explode, shouldn't it explode in the air? In the air. All right, anyways, I'll take it. I'll submit it here. All right, number 11. Oh, man, you guys got a decent amount of work here. At what height will the firework rocket hit its maximum height? This is when they want to set off the fireworks as high as possible here. Brainstorm ideas how to find the maximum height of this rocket. Well, here's where that trick is, guys. It's going to be pretty quick here. There's a trick to keep in mind And I think a lot of you guys know the trick actually in standard form, how to find the line of symmetry. Ah, yes, because I've taught you that a few times. I'm not going to say it right now. But what you did earlier here, what we did together, was we got the factor form. Yes, we did. Yes, we did. And remember that the factor form gives you the x-intercepts, gives you the roots. Where are my x-intercepts? They're at -1 and 5. So if I know my x-intercepts are at -1 and 5, I can actually figure out my line of symmetry. How? Okay, how? Well, line of symmetry, remember, line of symmetry can be located at the average of the x-intercepts. Remember, as we have symmetry, one side of the parabola looks exactly the same as the other side of the parabola. So we got line of symmetry at x equals, well, we got one 0, right? One x-intercept at 5, another one at -1. So 5 plus a -1 divided by 2, and this, right? 5 plus 1 is 4 divided by 2, and 4 divided by 2 equals 2. So our line of symmetry is at 2. Then the question is, what's our height? Well, we have an equation for that, okay? So here, brainstorm ideas. Okay, the line of symmetry, here we go. Line of symmetry is at x equals 2. So what can we do? What can we do? We know the line of symmetry, we want to get the vertex. Well, the vertex is on the line of symmetry. Vertex is always on the line of symmetry for parabola, okay? Looks the same on one side as it does on the other, so that's the highest points on the vertex. So line of symmetry at x equals 2. So let's substitute x equals 2 or t equals 2. I think t equals 2. Let's do line of symmetry is at t equals 2. T's our x here. So substitute t equals 2 into the equation and solve for h of t. Okay, check it out here. Here's my equation. Look, my equation here, we can plug in at 2 seconds in. That's when it's going to be its highest point. Mathematics, baby, because it's following that parabolic path. Allow us to solve for h of t. Okay, hit my equation button. Boom, hit there. Okay, I actually didn't need to do that. There we go here. And then I'm just going to replace this with 2. And you could have used the factor form here. That might have made your life a little easier. So, but I'm just showing you. I got my equation right here. You want to go back. You generally in problems want to go back to the original equation to use, the one that they gave you, so that you don't make any mistakes. Copying your other work or whatever. Okay, so now we got to plug and chug. We got to get this. Remember, use our PEMDAS rules. Parentheses, exponent, multiplication, division, addition, subtraction. It tells you the order of operations you can do this. So here, parentheses, we don't need to simplify. We just got 2 inside parentheses. Don't need to clean up parentheses. Next up, PEMDAS, exponent. Okay, so what I'm going to do is 2 squared. Okay, so I'm going to simplify that. So let's do that. Let's do h of t, and that equals -16. 2 squared is what? 4. And that's it. Now I've taken care of my exponents. There's no more exponents in this. 64 times 2 plus 80. And this looks kind of messed up here. But anyways, exponent done. So next up on PEMDAS, multiplication. So let's multiply. We got h of t equals -16 times 4 is -64. Okay, and then 64 times 2 is 128 plus 80. There we go. So -64 plus 128, well, that's just 64. So we did 2 times 64 a second ago. 64 plus 80 equals 144. Hopefully that's what you guys got. You know, I can't quote me, it's exactly right. So there it is, okay? The firework will hit the ground. Wait, hold on. Maximum height? What's it talking about here? So that's wrong. This shouldn't be in there. The firework is at the height of 144 feet. We know this because the line of symmetry is at x equals 2, right? And that's simply halfway. We just average them between the x-intercepts of the parabola, which are -1 and 5, and we substituted t equals 2, I should do t again, into the equation to determine h of t at the line of symmetry. which would be the vertex. Right? The vertex is the point on the parabola. It's on the line of symmetry. It should be the vertex. The vertex is the highest point. On the parabola. And I think I've justified it fully there. All right. Hey, it's ended up being a much longer video than I expected because it's it'll get stuck in the weeds here. So anyways, graph the equation for our fireworks situation. Check to see if you can see your solutions on the graph. How do you see when the rocket hits the ground? What is the maximum height? Let's do this. Let's grab it. I think I already had it there, so I didn't need to just copy paste it. I got to do H. Instead of H and T, maybe, let's see. Here, I got to get rid of these squiggly lines here. So it doesn't know X and Y. Oh, it does. There we go. So it knows that if you have H and T, it's a function of T. There we go. Let's check it out here. Hopefully I got it right. Ooh, it's narrow. Did I get 144 right? Let's check it out. Yeah! There it is. 244. Heck yeah. There's my vertex. Hey, there's my launch point, right? The y-intercept as we had it in the standard form. Must have been a point of point of interest here. 0 seconds in, that must be where it gets launched. It gets launched from a height of 80 feet, rises to 144, and then comes crashing down, unexploded. Stay away from it. Stay away from it. Got my x-intercepts there. Okay, there we go. There's your reflection here. Hopefully it's out. There's a lot to think about, but hey, I thought it was a good one to go through, especially because we're new to zero product property. You'll get more zero product property practice tomorrow, in case you're still not too sure about that. But hopefully you work through things successfully today. Message me if you have any questions. Thank you so much for watching. Bye.